Hello, I'm Gorash and I'm happy to present my most recent research results at the 8th International Conference on Very High Cycle Fatigue. The topic of my research is investigation of S275JR+AR structural steel fatigue performance in very high cycle fatigue domain. So my team consists of myself, Gorash. I'm research fellow at the Department of Mechanical and Aerospace Engineering at the research group VHCF Advanced Research Centre, University of Strathclyde, which is based in Glasgow, Scotland. Then Turul Chomlekchi is my departmental colleague who is principal research fellow. Then Gary Steiger, senior engineer from VHCF Minerals, South Africa. Then James Kelly, who is the senior technician at the Advanced Material Research Laboratory. And finally, Fraser Brownlee, my research group colleague, who is an expert in corrosion. I will start with introduction and motivation. Then most of the time I'll be talking about experimental setup specimens testing in application to S275 grade. Then we'll discuss current results and conclusions, and I'll finish with summary and outlook. Section 1. Introduction and motivation. About us. So we are Advanced Research Center. We are the research hub established 10 years ago between VHCF Group, which is headquartered in Glasgow, and University of Strathclyde, which is the oldest technical university in the United Kingdom. Over all these 10 years, we've been doing dozens of research projects on annual basis. And this year, we are celebrating 150 years anniversary of the VHCF Group that has been transformed into a premium mining and technology provider that helps its customers become more sustainable and efficient and deliver the essential resources demanded by demographic trends and fight against climate change. So it's all about sustainability, reliability, and helping to make equipment last longer. The equipment that we are focused on in this particular research is the one that's used for crushing and grinding, for classification and separation, and finally slurry transportation. When looking at available fatigue data for structural steel grades, in most occasions it's limited by 10 million cycles. And at some rare occasions there is a data available for over 10 million cycles, and even there are some extrapolations into gigacycle fatigue domain. The only problem with this data that it's quite generalized. So it's available for the whole group of structural steels and doesn't distinguish in between them with lower yield or higher ductility. And other thing is that it's also available for different weld connection types. When looking at these ascent curves closer, we can notice that they are extremely conservative because they guarantee 97% of reliability. And looking, for example, at the weld type W, we can see that in its corroded condition, the stress range is limited to 10 megapascal, so we are talking about plus minus 5 megapascal operating range for this type of welded connections. And this is of course extremely conservative. And this fact motivates our research to look at the particular grades, subgrades, in the gigacycle domain and investigate the real fatigue performance. In the focus of our research is grade 275JR as rolled, according to the European standard 125.2. When looking at its mechanical properties, we can see that there is a variation of yield and tensile strength, and typically what we should expect is 275 megapascals of yield strength and 400 megapascals of tensile strength. When looking at the ductility, its minimum requirement is 23%, but in reality it's a bit higher. When looking at the whole group of structural steel grades, including 2355, 355, 460 and 500, this particular grade 275 sits closer to the ductile types of the steel with low yield and tensile. It means that we should expect higher crack tolerance. The whole fatigue life splits into two phases. One is the crack initiation, which is described by the continuum damage mechanics. Another one is crack propagation, which is described by the fracture mechanics. And the whole question is which phase dominates on this one. We would expect crack propagation, but the comprehensive testing needs to be done to address this question. The plan was to study the fatigue performance of steel 275 using accelerated fatigue testing. So section 2 is fully devoted to experimental setup, preparation of samples and testing itself. But first of all, a few words about tensile testing. Tensile testing has been done using Instron 8802 servo-hydraulic testing machine, and the material properties such as Young's modulus, yield strength, UTS and elongation and break obtained at this testing were quite close to the values reported in the steel quality certificate. And it should be noted that such properties as yield and tensile strength and elongation and break were much higher than those required by the standard. The central piece of equipment is ultrasonic fatigue testing system VHCF8 from Shimadzu. This particular arrangement also included 5 kilonewton loading frame that allowed us to do fatigue testing at different R ratios. The expectation was to reach 1 billion cycles in 14 hours, when at the same time you would need 1.6 years to get to that value at 20 Hz using conventional fatigue testing. And other impressive value that it would be possible to get to 10 billion cycles in 6 days, and in the same time would take years and years of the fatigue testing at normal frequency. But reality appeared slightly different, and I'll talk about this in next slides. This is me on the photo in the middle of August last year, after the successful completion of the VHCF8 machine installation with the help of Shimadzu UK engineers. So it was quite challenging because of the lockdown restrictions, but we've made it together, thanks Shimadzu. And the next challenge was the material that we tested, because reliable thermal control was paramount. And the next central piece of this experimental arrangement is the thermal control measurement equipment. That's consisted of the PyroCube infrared temperature sensor that was looking at the sample, and a touchscreen display for PyroCube thermometer that could display temperature readings with the highest sampling rate of 1 second. Using the Excel spreadsheet provided by Shimadzu Japan and the material properties that we identified at our tensile testing, we managed to generate a correct geometry for the sample, so that the manufactured samples could resonate at 20 kHz. Another important thing that the shiny polished surface have very low emissivity, and that's why, to improve the emissivity and temperature readings, all the samples except those that are pre-corroded were painted into black matte paint. All the samples for this testing program have been manufactured at our engineering faculty workshops using the help of our skillful technicians. With some amount of persistence, the learning went quite smoothly, and all the samples manufactured could vibrate very close to 20 kHz. Again, as I mentioned before, all the available equipment have been used, and the the appropriate quality of the surface has been provided for the samples according to the standard. Apart from the samples with ideal surface finish, there were also two batches of samples. They were pre-corroded in a standard 3.5% sodium chloride solution, and they were submerged in water, first batch for 2 weeks or 15 days and second batch for 1 month. After that, the samples have been taken from this solution, cleaned from the rust and got prepared for testing. The good thing about these samples that they didn't need any painting because the emissivity of the surface was quite enough to get a correct temperature readings, and also the heat generation was much lower than with the samples with ideal surface finish. The surface roughness has been measured using Metitoya profilometer, and the roughness for 2 weeks appeared to be 12.5 micrometers on average. Here is a little bit more details about the second batch of the samples. It was important to protect the threads from the corrosion, and they were wrapped into the standard PTFE thread seal type that provided quite a good and reliable protection. Then they were kept in a seawater solution for 1 month to get a heavier layer of corrosion. And this photo shows that the layer of rust is much thicker than in previous batch. It was much more rust in the seawater solution as well. Then after the samples were taken from water, they were washed and cleaned, but still some rust remained on the samples as seen on this. When comparing the second batch of the samples with the first batch, the 1 month of corrosion with weekly washing has resulted in deeper pits that can be seen on this photo, and the roughness was 15.5 micrometers against 12.5 for 2 weeks of corrosion. So these two batches of samples also produce different fatigue testing results. So the next section tells about the obtained fatigue results. Section 3, current results and their discussion. This diagram briefly represents our expectation before we started this fatigue testing program. We were going to find high cycle fatigue domain with the standard fatigue limit and gigacycle fatigue domain with the different slope and maybe with the gigacycle fatigue limit. But the reality for this particular type of the steel appeared to be quite different. This slide represents the summary of all obtained fatigue testing results. That's why I would like to stay on it a little bit longer. The first group that I would like to draw your attention are the samples tested at 20 kHz. So purple triangulars are the samples where the crack originated from the surface, and purple squares are the sample where the crack originated from subsurface. There is an obvious fatigue limit for this group of the data, which is found around 350 megapascals. So the next group of the samples are two batches of pre-corroded samples. Purple diamonds are the samples that pre-corroded for 2 weeks, and yellow diamonds are the samples that were pre-corroded for 1 month. And there is a significant drop of the fatigue life in terms of the stress and in terms of number of cycles. However, there is one run-out sample for 2 weeks, but there is no run-out and no fatigue limit for the group of samples corroded for 1 month. Then the next group are the data points obtained at low frequency of 15 Hz. And the purpose of this data is to investigate the effect of frequency. So that has been done by finding the difference in between triangulars. So the data obtained at 20 kHz and the data obtained at 15 kHz, and this difference in average is roughly 170 megapascals. So that's the green line. So this value has been applied to the fatigue limit of 350, and it has predicted the fatigue limit at normal frequency at around 180 megapascals. That agrees quite well with the data provided from literature. So FKM fatigue data collection predicts the fatigue limit at roughly 190 megapascals, and the fatigue limit from grain data set is around 175 megapascals, which is quite a good prediction. And I should add that the actual fatigue limit found for this data set is around 200 megapascals. So the suggested frequency correction, slightly conservative, but this is quite good. This basic frequency effect correction has been applied to the precorroded batches in the same way, so it's just the difference in the stress, 170 megapascals. First of all, there was an extrapolation made to reach 10 billion cycles for both batches, and these are the values of 242 megapascals and 197 megapascals correspondingly. And then when the correction has been applied, the stress dropped to 67 megapascals for 2 weeks pre-corrosion, and for 1 month of pre-corrosion has dropped to 23 megapascals, which is actually quite low and conservative value. The biggest technical challenge in this research was the heat generation in this subgrade. The heat generation was so big that it's better to show it an example. The highest stress amplitude that these samples were tested was 400 megapascals, and this is one of the samples that lasted for almost 3 million cycles, and test conditions were that the size of the loading block was 0.1 second and the size of the cooling pause was 5 seconds. Cooling has taken 50 times longer than the loading block itself. With this kind of regimen, it was possible to keep the temperature in the room temperature range for half of the sample life, but then temperature exceeded 30 degrees and the temperature also peaked to over 200 degrees just before failure. It is also worth mentioning that the fracture surfaces of the failed samples were investigated visually and using two types of microscopy: optical microscopy and scanning electron microscopy. So with this help of these methods, it was possible to find the origin of cracks. The obvious advantage of optical microscopy is the coloring of the fracture surface that helps to track the crack growing path to its origin. The obvious disadvantage is the lack of focus and lack of resolution. The advantage of scanning electron microscopy is a perfect resolution, extremely high definition, extremely high level of details. However, the coloring is ignored. But with the combination of both methods, it's possible to identify the origin of crack with quite high accuracy. Section 4. Summary and outlook. I would like to summarize my talk with the following items. Parent and dry parent and pre-corroded condition of S275JR+AR grade have been investigated. Then the confidence and competence in running ultrasonic fatigue tests has been obtained. The duration of the fatigue tests have been limited so far by 1 million cycles, but the preparation to achieve 10 billion cycles is now in progress. Basic quantification of the frequency effect contribution has been done. Basic extrapolation of ultrasonic fatigue testing results into low frequency domain has also been done. Fracture surfaces can be examined using both optical and scanning electron microscopy. Heat generation remains the most significant technical challenge, but further investigation to more efficient air coolers and water cooling is in progress. Grade S275 will be tested for fatigue performance in welded condition considering mean stress effect and corrosion effects. And deep investigation of frequency effect ultrasonic fatigue testing application to structural steels is planned as the purpose of a new PhD project starting next year. So finally, big thanks to both Shimadzu UK and Shimadzu Europe teams for their technical support, and thank you for your attention.